Okay. So for the benefit of the recording and our viewing audience, we'll look at number 1 first. The number of milligrams in 6.6 kilograms. Okay, this is our starting point. We've got that many kilograms, we know. We want to convert the units to milligrams, and that necessarily changes the number that's associated with the units. Remember one of the things I said, if the size of the unit gets smaller, then the size of the number gets bigger. So you should expect to see a much larger number here once we get milligrams as the unit. Okay, so what we're into now is dimensional analysis. And the way I like to do it is say, where are you? Where are you going? So we're going to go to milligrams. To get there, we need a conversion factor that will change kilograms to milligrams. If you know what that is, we can do it in one step. Right? But if you don't know, then we can do a chain conversion. And I think I'll do a chain conversion here simply because it's a very useful technique. So what do I know about kilograms? Well, I know that if I put kilograms here, that's in the numerator, denominator, they cancel. And then in the numerator, we'll have left, I'm going to go from kilograms to grams first. Right? So 1 kilogram is how many grams? 1,000. 1,000 grams in a kilogram. See that little prefix? That means 1,000. Right? So 1,000 grams, I'll write it in scientific, is that. Okay, now we got rid of kilograms. Now we can go from grams to milligrams. And to do that, we need something that will cancel grams and leave us with milligrams. Okay, how many milligrams in a gram? And milli means 1,000th of. So if 1,000th, if a milligram is 1,000th of a gram, it takes 1,000 of them to make a gram. That. So now we got rid of grams, and there's our milligrams. So this is the thinking part. The rest of it is number crunching. And since our conversion factors are all powers of 10, we don't even need our calculator. Right? We just say 6.6 times 10 to the third times 10 to the third is 10 to the 6th. 3 plus 3. Okay? That's one of those rules you learned in math. If you multiply x squared times x to the third times x to the fourth, it's 3 plus 2 is 5 plus 4 is 9. Okay. As long as the base is the same. If it's a different base, then you gotta expand them and then put it together. But if the base is the same, you just add the powers. Okay? All right. So that's what I've done here. And the answer is this many milligrams. Now, since this is multiple choice territory, you look at the possible answers and see if it's in the right form. Right? Scientific notation, right? That's between 1 and 10, and then the power of 10 milligrams. Okay, so all our answers are in that format. So all we have to do is look for the one that matches. Right? 6.6 times 10 to the 6th is B. And of course, I'm using a key, so you already know the answer there. Okay? Did that throw anybody for a loop? Just need practice. Right? Practice these things. Right? If you don't practice them, then it's going to be sweat city for exams. All right, that was number 1. And then we look at number 2. Okay. Water has a density of 1 gram per milliliter. Well, round it off. Yeah, that's true. It's actually 0.99846 at this temperature, something like that. But we're rounding it off to 2 decimal places. So it's 1.0 grams per milliliter is the density of water. That's a good estimate. Which of these objects will float in water? Okay. Look at the question. Which of them will float in water? So what do you need to know to tell if something's going to float? You need to know its density and compare it to water. Right? In ancient Egypt, remember, ever hear of Archimedes? Archimedes, the story is that he was in Alexandria, which was the head city for the ancient world. Anybody who was anybody, if they needed to do research, they went to Alexandria because it had a massive library. And the reason it had a massive library was because let's see, at that time, maybe they still call them pharaohs, but the head honcho of Egypt dictated that any ship that stopped in their port had to turn over all their books. And those books, and they had to stay with them long enough for their scribes to copy them. And once they copied them, they'd give their books back. So they were accumulating books, scrolls, what we call books. And the Alexandria Library was massive. It had knowledge from all over the world. It got destroyed, of course, when the Muslims blew through. They burned everything down. At that time, Archimedes was there, and he was an intellectual. And the story was he had been thinking about this problem. Why do things float? And the story was that he was in his bathtub taking a bath, and it occurred to him, and he hollered, "Eureka! I found it!" Jumped out of his bathtub naked, ran down the street, hollering "Eureka!" And they probably didn't think twice about it because they probably knew his nature was kind of. Anyway, what he discovered was that if the object is less dense than the fluid in which it is submerged, it will float. And of course, it went deeper than that. He actually explained why it happens. But to answer this question, all we need to know is the density of these objects, whether or not they will be less than 1 or greater than 1. Okay? That's the reasoning behind this and how to answer the question. So if water, actually the density of water is 1 gram per milliliter, what about object 1, 2, and 3? Do we need to calculate that the actual density of these objects? The answer is no. We only need to estimate. Right? We only need to know, is it equal to 1, less than 1, or greater than 1? Right? We don't have to pull out our calculator for every calculation. To answer the question here, all we need to know is, how do we calculate density? It's mass per volume. Right? So for the first one, mass per volume of 69.4 milliliters is what? It's less than 1, isn't it? Right? 50 is smaller than 69. We know that one will float. How about the next one? 54.7 over, no, 60.9, 60.9 over 54.7. That's greater than 1. It'll sink. And the next one, 100 grams divided by 40 milliliters. That's way bigger than 1. Okay, so this is the only one that will float. It's the only one less than 1. That's why the answer is B. Okay. Problem solving. Right? Get there, the easiest way possible. First, you got to know what the question is. Which of these objects will float? And that question implies you need to know the density compared to the fluid in which you suspend it. Okay? We can do that with balloons too, but we need to know the density of air. And then we could calculate the density of whatever gas is in the balloon. But the question there is a little more complicated because you don't just have the object, the gas, you have the sack and you have the gondola. So we'll not go into that right now. Okay, that's number 2. Let's see, I'm going to scroll up to number 3. Let's see. I skipped 4, 5, and 6, so we'll just go up to 3. Like that. Okay. Convert a minus 12.2 degrees Celsius to degrees Fahrenheit. That's what that's saying. Fill in the blank. What is this in degrees Fahrenheit? Okay. So we have minus 12.2 degrees Celsius, and we want to go to Fahrenheit. So what do we need to know? We need to know what's the relationship between centigrade and or Celsius and Fahrenheit, right? And there's a formula for that, right? It's in that useful information in the document, last page. And like I said before, if it's here, it'll be available on the exam. If you come in here and take a paper exam, it'll be on the back of the exam. If you take it in Brightspace using Respondus Lockdown Browser as your proctor, then there should be another file in that same folder with the exam, with this information in it that you need to print before you open the exam. Because once Lockdown Browser gets hold of you, it's not going to let you access that information. So you need to print that out first. Then you'll have it, and then you can go do your exam, and you'll have this useful information. But if you look over there on the far right, formulas, there's the formula for the relationship between Fahrenheit and Celsius. Now here's the way I remember it. Fahrenheit equals 9/5 Celsius plus 32. 9/5 is 1.8. So it's written as 1.8. So actually, for estimation purposes, this is more useful for me. You ever drive by a bank and they've got their logo up there, and it's got a big thermometer, right? It tells you what the temperature is at that location. Well, usually now they'll flip between Celsius and Fahrenheit. But if you're driving, you might be by and you only see one of them because you're not going to stop traffic just to read the temperature. So if the temperature says, I don't know, 20 degrees Celsius, which is a nice temperature actually, 20 degrees Celsius. What does 20 degrees Celsius mean? Well, if we plug 20 in here, 5 into 20 is 4, and 4 times 9 is 36, plus 32 is 68. So I've done this often enough. I know that 20 degrees is 68 Fahrenheit. I just know it. Right? So if it says 25, it's gone up 5 degrees Celsius, but 9 degrees Fahrenheit. So 9 plus 68 is 77. So I know if it says 25, it's 77. So that's why I like 9/5 better than 1.8 for estimation purposes. But let's get back to the question. We want to find out what this is in terms of Fahrenheit. So it's already solved for Fahrenheit. That's good. So now all you have to do is plug in. Well, we use the one that's in the book. 1.8 times minus 12.2 plus 32. Okay? This is algebra, right? Solving for an unknown. There's your unknown right there. There's your known. This is a variable that we happen to know the value for it. We don't know this one. And any formula that has only one unknown left, you can solve for it. Okay? Are you puzzled? Okay. Have you had algebra?
I really.
Long time ago?
Yeah.
Okay. We use algebra, but we're not going to use everything that you learned in algebra class. Just a few things, and this is a refresher, right? How do you solve for this one? Well, we know that it's already solved for us for Fahrenheit. So we just need to plug in the values for the unknown, right? So this one is 1.8, this one is minus 12.2, and then you add 32. So you just multiply these two together and add 32, got your answer. All right, so let me get my calculator. We'll do a step at a time. 1.8, this is where you need to know how to operate your own calculator. And then 12.2, but we need the negative sign, times. All right, so this part is going to be minus, here, this is minus 21.96. That's 32. Now, 32 can be taken as our significant figures. That's an exact number. So it will not limit these values over here. Right? So really what you've got is three significant figures, we have to round this one off. Minus, that rounds this one up to 10. So that makes this one 22.0. If we round it up. Okay? Well, I shouldn't have even looked at that one, just this one. If we round it to 3 places, no, that's right. Sorry. Round it to 3 places, this is greater than 5. So that one goes up to the next one, which is 10. We have to carry the 1. So 22 minus 22 is this value. And then plus 32, which is an exact number in this case. Right? So it will not limit. We don't have to do that. Keep that. Oops. Let's get the negative sign. So 2 from 2 is 0, and 2 from 3 is 1. Minus 10, 0. Here we go. Whoa. Oh, plus, this is bigger than. Am I confusing anybody? Sorry. This is smaller. This is negative. Subtracted from 32 is 10. That's why I use the key for these discussions, because they keep me honest too. See, mine answers, minus 10 is nowhere on there. Right? So I look at myself, oh, I made a mistake. And you can do that during an exam too, especially if it's multiple choice. If you get an answer here that's not there, maybe go back and look at your calculations. So 10 degrees Fahrenheit is minus 12 Celsius. That's what that's saying. What if we had Fahrenheit and wanted to go Celsius? Well, you got 2 choices. You can plug in the value for Fahrenheit and then solve for this one after you get the number in there. Or you can solve using algebraic rules, solve for this one, and then plug in that. So if we do it that way, we got to get this one on that side first. You got to get the additions and subtractions on one side, away from the term you're solving for. So this would be Fahrenheit minus 32 equals 9/5. Okay, you just subtract 32 from both sides. Anytime you do the same operation to both sides of the equal sign, it's kosher. It's valid. Okay. Now, in order to remove that fraction, we say we multiply both sides times 5. Right? And that'll get rid of the 5 there. So 5 times f minus 32 equals 9c. And then we divide both sides by 9. It gets rid of that 9. So now we have 5 nines. F minus 32 c. Now we solve for c. We just plug in the value of f, and you got your answer. Okay? Practice, practice. And let's see, there should be, let me check to be sure. Okay. I was looking at my worked problems, the one where I hand wrote out the answers. That one's here. Sometimes you might see some of these might be skipped. You may not have a worked problem for a number, given number. If that's the case, then it's a matter of memorization and doesn't require any explanation. Okay. All right. So that was number 3. And I think the next one is number 7. Let me flip the page over. Yep. Next one I want to look at, number 7. Oh, okay. Let's see, come on. Almost. Number 7. This is a case where we do solve. Go from Fahrenheit to Celsius. Okay. So I could put the formula that we converted up here before, but what if we do it this way? What if we just plug in a value for C there and then solve it? It's for Fahrenheit and then solve it for C. So Fahrenheit is 232.0. Okay, equals 9/5 C plus 32. Okay. Next thing we do is subtract 32 from both sides. So that's 200.0 equals 9/5 C. So I subtract 32 from this side and from that side. Now, if we say 5 times this, right? 5 times that, 5 times that, we could write it like this. 5 times the whole thing. Right? That cancels this one. And 5 times that is 1,000. Equals 9C. Then we say C. Well, that may be confusing. Let's keep C on this side. And we divide this one by 9. So 9 into 1,000 is what? It's 111. 111.1. Or 5 significant figures. Well, let's see what the answer says. Choose the best answer. 111.1 is the best answer. We should be able to, oh no, 4 significant figures. There we go. Because this has got 4 significant figures, 5 times that is 4 significant figures. So that's true, 4 here. So that's degree C is our answer. Okay. That was 7. So we've gone both directions. Centigrade to Fahrenheit, Fahrenheit to centigrade. I say centigrade, that's, I think they call it Celsius now. Named after the inventor. 9. Yeah. 9. Which of the following describes the chemical property of gold? So another thing about these multiple choice questions is look to see if there are any that say all of the above, none of the above, two of the above, only A and C, those type of squirrely ones. Because if they do, then you'll have to look at every one in order to eliminate those oddballs, none of the above, all of the above, so forth. But if you've got unique answers for each one, then you can just work your way down, and when you find the right answer, you're done. I'm trying to help you get through exams quicker. Okay, which of the following describes a chemical property of gold? Gold is a very dense metal. Does density have anything to do with the chemistry? No, it's just mass per unit volume. That's it. That's a physical property. Gold is a soft metal. That's a physical property. It talks about the potential for malleability. And you're not actually changing the gold. You're not doing anything to the gold. You're not reacting it to make a new substance. It's still gold. Gold is an inert, non-reactive metal. That speaks to the fact that gold will not react chemically with other elements or compounds. Well, actually it will, but you kind of have to force it. How do you get gold into solution? Well, one of the ways you do it, and this just dissolves it, this doesn't convert it into anything. Actually, it does. Is use a mixture called aqua regia, which means royal water. And it's composed of hydrochloric acid and nitric acid. And those in combination take gold into solution. And actually, it forms the chloride of gold. So it is a chemical reaction. But being non-reactive is a property of gold that speaks to its chemical behavior, right? Its potential. And we can stop there. If we looked ahead, we say gold is yellow, right? That's physical. Gold is a good conductor of heat and electricity. It doesn't change the gold. It just says it will conduct heat through it very easily or conduct electricity through it very easily. Doesn't change it at all. So C is our answer. That speaks to a chemical property of gold. Number 9. All right. Let's see. I'm going to skip over to number 12. Let's see if I can page down. There we go. All right. Well, okay, we're going to add in the sum of this number and that number, the number of significant figures is. Remember your rules for significant figures in operations. You got 2 types, multiply, divide, which includes powers also, and add, subtract, 2 different rules. What do you got here? Got add, subtract. Right? So how do you add these together? Because you can't just look at these and say, what are the significant figures? If it was multiply, divide, yeah, we could do that. Just like that, we could say, how many significant figures in the answer, but not add, subtract, because you have to line up the decimals. Yeah, 45, 66. Add those together. Got our decimals lined up. That means we can keep everything. They both have hundredths place. So we can keep everything from here over. So 4 and 6 is 10, 1 and 9 is 10, carry 1, another one, and there we go, like that. Right. So these may have 4 significant figures, but the answer has 5. Because we can keep both of those decimal places, we've got 5 significant figures in the answer. Okay. I don't know how many students look at a question like this And they automatically say 4. Because they don't realize, they don't remember that this is not multiply, divide. This is add, subtract. It's a different set of rules. All right, that was 12. Let me see. Skip down to 15. This is which of the following is an element? Okay, so this probably won't have an explanation in my written. I'll just bet 15. Actually, it does. Okay, 15. What do we have to choose from? Which of the following is an element? Remember the definition of an element. An element cannot be reduced any further by chemical means. Okay? So can we simplify this one by chemical means? Yeah. Break it apart. We can react it with oxygen and make carbon dioxide and water. We can change it chemically. Salt. What's salt composed of? Well, I assume we're talking about table salt, sodium and chlorine together. So that's a compound also. This is a compound, that's a compound. How about helium? Helium is an element. Now, where's another clue? Whether you've got an element or not. Can you find it on the periodic table? Okay, there it is. Helium's there. Sugar's not there, vinegar's not there, salt's not there, and alcohol's not there. So that's another way to answer this question. Helium cannot be reduced any further by chemical means. So it's on the periodic table. What's the abbreviation? What's the symbol for helium? Remember? Have you got that far yet? It's one of the easier ones. Big H, little e. Okay. Now, why is it called helium? Because the discoverer, if you discover a new element, you get to name it. And the discoverer located helium first in the atmosphere of the sun. Right? In Greek for sun is helios. So he said, okay, there you go. I mean, it just makes sense. That's where I found it. So I get to call it from the sun, helium. Later on, we found it on Earth. Where's the most abundant source of helium? You probably don't know this. It's not in the atmosphere because it's a very light gas. Right? So it's going to be like that. Any helium that you find in the atmosphere is going to be trace amounts. And it's so light, it just blows off into space. So our economic source of helium comes from natural gas. It's trapped in the earth. So when we clean up natural gas, we take the 2x4s and dead bodies out of it. And then we take water, we dehydrate it, and then we recover helium from it and stockpile it. At one time, helium was a strategic element because it was used in dirigibles, balloons. And we had the only source, the most abundant source of helium was in the United States. And we said to Germany, because you're on the other side and you're a belligerent, you can't have any, right? So that's why they're Hindenburgs, the big balloons, that's why they filled them with hydrogen, which made them float. In fact, hydrogen is more efficient than helium. It's just one problem. It has a chemical property called flammability. And eventually it did. That's what then the Hindenburg in New Jersey, they still don't know why, caught fire and just burned up in just a minute. Anyway, that's aside. 15, how about, let's see, 18. Got a page to 18. There it is. Okay. Remember when I said there a large number of chemical problems can be solved mathematically. Dimensional analysis can solve them. As long as you don't violate any rules of chemistry and physics, then math can be your avenue to solution. How many liters are in a 29 ounce bottle of pop? Okay, that's our starting point, 29 ounces. And we want to know how many liters that is. Right? And liters is a capital L. Right? You'll see in some older literature a little L for liters. That's wrong. It's a capital L means liters. Okay, so we got 29 ounces and we want to go to liters. So we need conversion factors. Well, here's a clue. You're given two conversion factors. We can go ounces to quarts, and then we can go quarts to liters. So that's a chained conversion. Just put them in the right order, get rid of ounces, and leaves you with what? Quarts. So we're still, I think they call it the imperial system, or the English system. So 32 ounces goes down here like that, and that cancels ounces. Remember, this is a conversion factor. Conversion factors are equal to what? 1. Always equal to 1. So you can say this times 1 times 1 times 1 times until you're blue in the face. But we want to substitute in and say here's something that's equal to 1 so that it'll do what we want it to. So this cancels ounces and leaves us with quarts. Now we want to use quarts to liters because liters is where you're headed. The numerator is where you're headed. The denominator is where you're coming from. So we're coming from quarts. Oh, we need the number 1.0567. Oops. That's right. 1.0567. There we go. So now we've got liters. Cancel everything else out. That's the thinking part. Now we crunch numbers. So in mine, I say, my calculator, I say 29. And then I say 1 times 1, all right, so that's a no-brainer. Divided by 32. And divided by 1.0567. And I get 0.857622. Now, is that the right answer? That's too many decimal places. So we need to round, right? This is a conversion factor. That's an exact number. That's an exact number. This is the only one that influences the significant figures in your answer. 2 of them. So we round off to 2 right here. Right, that's 7, so this means 0.86 liters. Okay? And there she be right there. All right, that was 1820. 20, which is a homogeneous mixture. Okay, we had an example like this during the lecture. And what did I do? I worked backwards. Which ones are mixtures? If it's not a mixture, you can throw it out, right? Process of elimination. That's a mixture. That's an element, throw it out. That's a mixture. That's a pure substance, right? Throw it out. It's not a mixture. That's a mixture. Right? So we can say A, C, or E. It's got to be one of those because those are the only mixtures in that group. Right? Then we look for homogeneous. Which one's homogeneous? Well, we can eliminate the heterogeneous ones. Soil's heterogeneous. Jelly beans are heterogeneous. So that leaves gasoline. That's the only one left. That's homogeneous mixture. Hey. 22. Here she is. Let's see. This one's going to be a little more complicated. And the word problems, everybody loves word problems, don't they? No. Word problems, the primary purpose of a word problem is to confuse the test taker. And if it doesn't confuse you, that means you understand the material. And you know what stuff is just blue smoke. It's just blown in your face to confuse you. So we look at the, read through the problem, and then we say, what is the question? A graduated cylinder. What's a graduated cylinder? We haven't talked about that. A graduated cylinder is just that. It's a cylinder. Okay. And it's marked off. It's graduated. And it's marked off in milliliters, volume. So it's to contain. That means it starts at the bottom with, well, it depends on the cylinder. Let's say, which one would this be? In milliliters. So this is probably 1, 2, 3, 4, 6, 7, 8, 9, and 10 milliliters. So it's going to have subdivisions in here, tenths of milliliters. All right, a graduated cylinder contains 20 milliliters of water. Well, that's a bad choice. Anyway, if it contains 20 milliliters of water, let's just say it's like this, this, this. Say it's got, this is 20 milliliters of water. Sometimes it helps to draw pictures. That's where it starts. An irregularly shaped object is placed in the cylinder. Right? And we have to assume that it doesn't absorb water. It just displaces the water. The water level rises to 31.2 milliliters. Right? After we put this in. Now it's at this level. Okay? If the object has a mass of 80.4 grams, mass is equal to 80.4 grams. What's the density? That's the question. What is the density? Right? So what do we need to know to answer that question? How do you calculate density? Density is a formula. Mass per volume. Okay? So now we look to see, do we have the information we need to solve for that answer? Yep, we've got mass. Check that off. How about volume? What's the volume of the object? The volume of the object is the displacement. So the volume of the object is, well, just do this. Okay. It's the difference. 11.2 milliliters. Okay, so now we got volume. Now all we have to do is just plug them in. That's the thinking part. And calculate the density. This is given to us as 3 significant figures. We use our subtract rules, right? Line up the decimals. That's good, 11.2. So that's 3 significant figures. And 3 divided by 3 means our answer has to have 3 significant figures. So we say 80.4. So my calculator tells me 7.178571 grams per milliliter. So we're obviously going to have to round off to 3 significant figures. 1, 2, 3. Right there. That's 80. That means it should be 7.18 grams per. And there it is right there. Okay. So the reason this one is more complicated is of that right there. It's irregularly shaped object. We can't just take a ruler and measure dimensions and then calculate volume. We have to use this trick, displacement. All right, let's see, 22, 25. We'll look at 25. There it is. What Kelvin temperature reading equals 61.2 degrees Fahrenheit? Right? So the question is, what's the Kelvin temperature? Okay. And if I didn't mention before, it's not degrees Kelvin. It's just K. It's Kelvin. So many kelvins. All right. We can't go directly from Fahrenheit to Kelvin. We got to go to Celsius and then from Celsius to Kelvin. So what we need is like that. Solve for Celsius. F is 32. 5/9 equals that. And then we need to know the relationship between Celsius and Kelvin. So Kelvin is equal to Celsius plus 273. Right? Well, there are more decimals out there, but 273 is good enough for us. Okay. Now, we could combine these and say, okay, we know what C is. So we can take this part equal to C and go stick it right in there and do the whole thing in one calculation. Or you can do this calculation to find out what C is. 5/9, 61.2 minus 32 equals C. Let's see what that is. Right? Remember, 32 is exact. So our answer will come out 61.2, 2, and 5/9. So I get 16.2. See? And then we plug this one in here, there, and add 273 to it. 273 is an exact number also. So we get to keep our decimal. So it's 28.9. Nope, sorry, 289. 289. Okay. And the best answer for that, well, actually mine says 0.2. That says 0.4. So in multiple choice tests, pick the best answer. And this is the best answer. It's probably a rounding error, or they use 273.15, which is the extended version, or 0.147. More decimals in that conversion. That's where that difference is. Okay? That was 25, 26. It's already up there. 26. Yep. Which of the following processes is a chemical change? Now we're talking about the actual change, not the potential, not the property, but actually something is happening. A substance is becoming a different substance. Its identity is changing. So we're looking for that. Dry ice sublimes were left on the demo table. It's just going from solid to gas. The light on a candle burns until a bell jar is placed over it for a period of time. Yep. That candle is burning. It's converting paraffin into carbon dioxide and water and a good bit of soot too. It's an incomplete combustion. So this is a chemical change. Right? You're going from paraffin to different substances, gases. Right? So none of the above processes are chemical. Right? We found one that was. So it's not this one. It has to be that one. Because you don't have two of the above, you don't have three, you don't have A, B only, or C. You know, you don't have those weird ones that we like to throw in there and confuse you. So we found the answer right here. Red food coloring, that's a physical change. Liquid nitrogen dumped on the floor vaporizes, that's a physical change. The identity of the substance did not change in those processes, but it did change in this one. Okay, so B's the answer for 26. Let's see. There's some redundant ones. Let's skip down to 30. 30 is a test of your memory. Which metric prefix is used to designate 1/10? And remember your prefixes. Well, let's look at these that are given. A, B, C, D, E. Big M, little k, little c, little m, d. But what does this one mean? This one means mega. It's equal to 10 to the 6 times, whatever the base unit is. Big M in front of it means it's actually unit's actually 1,000,000 times bigger than the base unit. This one is kilo, which is 1,000 times. This one is centi, which is 10. 110. No, 100. 10 to the minus 2. This one's milli. 10 to the minus 3. This one is deci. The minus 1. 1/10 designates 1/10 of the base unit. So a decimeter would be 1/10 of a meter. Or a deciliter would be 1/10 of a liter. It's not used very often. More common ones are the kilo and milli and centi, centimeter. That's used pretty often. Mega, well, yeah, mega is used sometimes. Megabytes, computer. And we've left megabytes behind. It's in the dust. Even gigabytes are behind now. It's up to terabytes. Okay. Test your knowledge of prefixes. Let's see, skip down to 36. Yep, there it is. 36. The volume in milliliters occupied by 41.9 grams of mercury, which has a density of this, is what? Okay. So the question is volume. What's the volume? If we know the density and we know the mass, we can find the volume because of this formula. Okay? We want to know the volume. So if we solve for volume, we get mass divided by density. Right? These two just swap places. And when you cross the equal sign, the term goes into the denominator if it's in the numerator. If it goes in the denominator and it crosses the equal, ends up in the numerator. Okay. And we can prove that. Right? If we want to put volume on this side, we just say multiply the whole thing by V. Right? So we get V on this side. and we cancel V on that side. That's how that works. And for D, you want to divide both sides by D. So we cancel D on this side, and it ends up on this side. Okay. I'm just proving. So you don't have to take my word for it. Okay, so we know the formula. We solved it for volume, right? That's what we're looking for, volume. But while we're at it, density is in 13.6 grams per milliliter. And mass is 41.9 grams. Okay, so what's that going to do? Is it going to give us the right units? Well, yeah, there's the milliliters. And notice that this is in the numerator and this is in the denominator. So the grams cancel. But what about that milliliters? It's in the denominator of the denominator. So in mathematical terms, the denominator of the denominator is the numerator. It's just like saying this milliliter is up there, actually. Okay? So if we cancel this, now we got milliliters on the numerator. And all we have to do is divide 13.6 into 41. So that should be in the neighborhood of 3. Okay. So I get the answer by estimating it and looking at the choices. Right? That's too small. That's too big. That's too big. This is the only one that comes out. 13 into 41. Right? What's 3 times 13? 39. So bump it up a little bit. Yeah. Estimation can save you a lot of trouble. Okay. About 40. 40. How many significant figures are in this number? Let's see, 40090. Significant figures. All right. We know that all non-zero numbers are significant. And then there are the zeros. So the zeros, it depends on where they're located. Right? Leading zeros are never significant. So those 3 are not. Okay? Captive zeros are significant. Always. They're between 2 non-zero numbers, they're significant. So we've got 1, 2, 3, 4 so far. And trailing zeros are only significant if there's a decimal, an explicit decimal in the number. There it is. So 1, 2, 3, 4, 5 decimals. 5 significant figures. Okay? What if, teaching moment, what if I move the decimal over here? It's a different number, obviously. Do we still have 5 significant figures? Yep, because there's a decimal right there. If I accidentally left that decimal off, oops, now we only have 4 significant figures. All right, that was 40, 41. Another prefix question. Factor of 10 to the minus 2. We covered that one earlier. Right, so can we find the 10 to the minus 2 in here? There it is right there, centi. Centi means 100th of, which is 10 to the minus 2. So a centimeter is 100th of a meter. And it's about like the distance between those 2 marks. All right, that was 41. Let's see, 47. Page down to 47. Yep, there it is. Drink. The result of the following calculation has how many significant figures? All right, we're looking for the total number of significant figures in the answer. So, what do we have here? We have a mixture, right? We got to add, we got to subtract here, and we've got to multiply and a multiply there. Okay, the units don't matter, not for the answer to this question. So we can focus on the numbers only. All right. So what do you do first? Well, I remember that from math class. Order of operation. Parentheses come first. If you've got parentheses identifying operations, do them first. So we've got an operation inside the parentheses here that has to be done first. Okay. And then you can do the rest. Parentheses, exponent, multiply, divide, add, subtract. So let's see, 33.12. And then we're going to subtract 31.12. Okay. Line up the decimals. So that's 0, 0, 2. That's it. Plus 2. 3 significant figures. Right? Okay. If we've got 3 significant figures, let's do it like this. Now we've got multiply, divide rule. 3 significant figures here. How many in this one? 4. How many in this one? 4. That one determines the answer. Only 3 significant figures in the answer. We don't even have to do the calculation now. We had to do this one in order to find out how many were in that term. And then the rest of them, you can just use the multiply divide rule and say the least number is the limiter. Okay? Saves you a lot of time on the exam. You don't have to calculate the whole thing out. All right, that was 47. Page 48. Ooh, have to scroll this one. 48. Which is an example of a homogeneous mixture? Well, let's see. Soil and dust, they're all different particle sizes, so we know they're not homogeneous. Sodium chloride, it's not a mixture, that's a pure substance. It's a compound. Aluminum is an element. Vodka. It's a mixture of ethanol and water and some other stuff. And oily water, that's definitely going to be heterogeneous with the oil floating on top probably. So vodka is our homogeneous mixture. Booze is homogeneous mixture. Wine is a homogeneous mixture. Beer is a homogeneous mixture. 48. Let's see. Skip past some redundants and go to way down. 68. See how close I can get. There it is. 68. A cubic centimeter is equivalent to what other metric unit? This is memorization. I mean, we proved it in the lecture, but what is a cubic centimeter equal to? Out of this list, it's not equal to a liter, not even equal to a deciliter. Oh, there it is right there. 1 cubic centimeter is 1, oops. I would have got that one wrong. That's a unit of length. This is unit of volume. milliliter. Milliliter. Okay, those are equal. So if you're in a hospital that's been around for a while, and you look at their storage or some of their products, I guess if they're hermetically sealed, they're okay. And you can use them, they'll be cc's, like a 10 cc syringe. Right. Now they'll be 10 milliliter syringe, but the older ones said cc's on them. Cubic centimeter. It's exactly the same thing. Same volume. How about 71? The state of matter of an object that has a definite volume, but not a definite shape. Right? Well, we have three states that we discussed: solids, liquids, and gases. So a solid has a definite volume and a definite shape. A definite volume and no definite shape is not a trick question. It's a liquid. Right? How do you know? Well, if you pour a liquid out on the table, it's just going to go everywhere. No definite volume. So that's why the answer is here. All right. Let's skip down to 84. Okay, we've got this beaker. And the question is, what's the new volume of water in the beaker? Well, how did it get to be a new volume? Well, we added 20 milliliters of water from a graduated cylinder to the beaker. This speaks back to the place in lecture where we talked about what determines the accuracy of your answer. It's the least accurate device in the sequence of measurements. Now, this one is accurate to, well, a tenth of a milliliter is the last digit in that number. And just as a reminder, which one of these are certain? Those are certain. This one is uncertain. In other words, it's an estimate. It's a guess. So how about this one? If we're going to put that into this one, is this one any more accurate? Right? Between 10 and 20? The markings are only every 10 milliliters. Right? So we're only going to be able to estimate to a milliliter, somewhere in between here. And the last one's a guess. So it's between 10 and 20. That means this one is certain. But this one, the ones place, is a guess. So what is it? Well, let's just say it's 5. Oh, yeah, 5. Between 10 and 20, halfway between them, it's 5. So that's what we're starting with, and we're adding this to it. Right? So if we say 35.0, we can only keep that much of it. And rounding off, that's a 0, so this is 35. So that's why the answer is 35, not 35.0, because this limited the accuracy of our answer. Okay? I had a friend of mine tell me, I didn't know this person, but it was in a different department at Louisiana State University in the Marine Science Department. And this is no reflection on the country of origin, but he was a foreign student, exchange student. And he wanted to measure out a volume of some reagent. So he had a graduated cylinder, and he had a volumetric pipette, which was accurate to, let's say this is 1 milliliter, 1.00. And this graduated cylinder is accurate to maybe 1 milliliter. So he needed 21 milliliters. So he had 20 milliliters here, and he added that one to that one and claimed that his volume was 20, 24, 0. Now, if his advisor, if this is a graduate student, his advisor let him get away with that, and his advisor ought to lose his tenure or whatever, because that's not right. You might get close to 21.00, but you're not going to be there. Okay? Real world experience. Let's see, 84, we did that one. How about, oops, must be a lot of repetition here. Let's get to 94. Here we go. 94. Which of the following is only a physical change? Okay, now, here's one of those goofy ones. E says at least 2 of the above exhibit only physical change. That means you got to check all of the ones above. So we can't just find the answer and stop. We have to do all of them. Which of the following is only a physical change? A, B, C, D. Okay, A. Leaves turn colors in the fall. Well, based upon what we can observe, it looks like a physical change. If you get down to the biochemistry, you know it's a chemical change. But what we can observe, that's a physical. Okay. Okay. Read it again. Which of the following is only a physical change? This is physical and chemical. Okay. A banana ripens. That's definitely a chemical change. What causes bananas to ripen? We know that now. It's a gas called ethylene oxide. So when bananas are coming from, say, Honduras on a boat, they pick them when they're just barely starting to turn yellow, but they're still mostly green. And they stick them in the hold of the ship, and they keep them from ripening by having a vacuum pump going and squirting some nitrogen in there to displace the oxygen and the ethylene oxide. And that keeps them from ripening. And then about 3 days before they arrive at port, they start pumping ethylene oxide in there in the container. And the bananas ripen. By the time they get to port, they're almost all ripe. But it's a chemical change. It's a biochemical change. Cookies burn in the oven. Sugar dissolves in coffee. That's physical only. You're just taking the sugar, busting it apart, and hydrating it in the coffee. So D is the only one that's physical change only. It's not a combination. Let's see. Well, while we're here, 95. How many significant figures are in this number? First of all, recognize that that's scientific notation. And the beauty of scientific notation is if you do it right, you're only going to have to look at, no matter how big the number is in standard notation, once you get it in this form, all you have to do is look at the coefficient, 3 significant figures. So there it is. What would that be in standard notation while we're here? which way does the decimal move? If you stored up 1,000 here, this number needs to get bigger if we decrease this one down to 0, which means it's equal to 1. Then this one would be 1, 2, 3. 1,890. Oops. I can't do that, can I? Because that's only 3, so I have to, that's not significant. 1,890. All right. Let's see, how about $107? I'm going to scroll that one a little bit. Okay, fill in the blank. A blank is a summary of observed behavior. And a blank is an explanation of the behavior. This goes back to the very beginning of our discussions. The difference between a physical law and a theory. A physical law is a summary of observed behavior. It can be expressed in terms of just a pure statement, like Newton's first law of motion. An object in motion tends to remain in motion unless acted upon by an external force, and an object at rest tends to remain at rest unless acted upon by an external force. That's just word statements. Whereas second law just says if a mass of a given size is accelerating at a certain rate, then that is a consequence of a force. So that's why the second law is in the form of a formula. But it's still a law. It just says what happens. It doesn't make any attempt to explain why. Whereas a theory tries to explain why something happens. And usually it's accompanied by a model. It could be a mathematical model, it could be a physical model, it could be something in words. A model is a representation of the system in such a way that you can make changes to the model and see what that effect has on the outcome. That's why theories are much more powerful. Okay, so the answer to this one is the law is a summary of observed behaviors and a theory is an explanation of the behaviors. And next one on the hit parade is 114. There you go. Your friend is 5 feet, 9.8 inches tall. 5 feet, 9.8 inches tall. What's your friend's height in meters? What do we have to do first? Well, we've got 2 units of measure here. I mean, it's an expression of the height of a person, but it's in 2 different units. So we've got to put these together into a single unit. So do we want to go feet or inches? Well, it depends on what you know about the conversion from the English system to the metric system. For me, I know the relationship of in inches to centimeters. I just have it memorized. So I would go to inches here. So 5 feet is 60, right? 60 inches. 12 inches per foot, 60 inches. And so we have 60. $69.8 inches. Now, I just violated a rule because this is 60. It has two significant figures here. So 2 here, but line up the decimals, that means it's really only 7. Okay, that's 70 inches. Now we can convert to the metric system. Right? I know the relationship, inches to centimeters. Right? 1 inch is 2.54 centimeters. Right? Now that I've got it in centimeters, I can convert to meters. Let's do it down here. Centimeters on the bottom, meters on the top. So how many centimeters in a meter? 100. Okay. So 70 times 2.54 divided by 100. So I get, let's see, two significant figures, 1.8. Rounded off, 1.8 meters. There it is. Okay. So what was the question? What's your friend's height in meters? We're headed for meters. What are we given? We're given feet and inches, right? So you got to get from one place to the other. How do you get there? You get there like that. So it's not just a matter of memorizing formulas. Formulas are valuable. But if you memorize a formula and try to pigeonhole, shoehorn numbers into the formulas that you know, more often than not, you're going to get it wrong. Formula is good if you use it for the right purpose. 116. Here we go. Which of the following is an incorrect description? Okay. In the phrase, do the words go together? Okay. Homogeneous and mixture. Yep. Those fit. It's a description of a particular type of mixture that is homogeneous. A solid element. Yeah, that works too. Elements can be solids, they can be liquids, they can be gases. A solution of gases. That might be tricky, but it's true. We breathe a solution of gases every day, in and out. We breathe in nitrogen and oxygen primarily, and we exhale carbon dioxide and water and some oxygen. When you inhale and exhale, the amount of oxygen, how much oxygen is left? If oxygen is, say it's roughly 20% coming in, how much is going out? About half of that, 10%. That's why when you do CPR, well, it used to be CPR, you would breathe and compress. But they discovered that there's enough oxygen in the person's tissue that as long as you just compress, you'll keep extracting oxygen from the rest of the body and sending it to the brain, which is the real problem area. That's the first thing to go. What is it, 4 minutes or 5 minutes without oxygen, your brain starts to die. So now we don't do any breathing. And a lot of people probably like that because when you start compressing somebody's chest, what are they going to do? They're going to throw up. You don't want them throwing them up on you. So just do compressions to the beat of staying alive, right? Okay, back to the topic. Okay, we got down to solutions of gases, a mixture of solids. Yeah. Right, you can have a mixture of solids. You could have solid jelly beans. You could have a solution, a mixture of solids, like brass, alloys are mixtures of solids. Heterogeneous compound. Nope. Compounds are pure substances. There's no mixture about them. So heterogeneous and compound do not fit. They don't go together. So that's the answer to this one because it's wrong. How about 119? Okay, here we go. Let me scroll down a little bit. What you see on the right-hand side is what we call in chemistry a burette. There we go. A burette is a device, 119, yep, 119. A device for delivering accurate volumes of liquids. So that's why you'll notice that it's the volume, and this is in milliliters, the volume is numbered from top to bottom. Because if you start at 0 and you deliver some, then all you have to do is read off and you know how much volume you delivered. Whereas a graduated cylinder is to contain, so it's graduated from the bottom to the top. Whereas burettes are the other way around. Okay, that's important because it determines how you read a burette. What's the volume? Using 0 as your reference point, how much liquid has left the burette? So if it starts at 0 and goes down, it's past 20, but not 30. And we have, this is 1, 2, 3, 4, 5, 25, 26, 27, 28, 29, 30. So each one of those little marks is 1 milliliter. Okay, so we can say, all right, we delivered definitely 20, and we're past 1, 2, not to 3. So we're sitting on 2. So those are the marks that are certain. Those are certain marks. 22 is certain. So we can estimate the last one. Okay? 22.0 milliliters. Because the last one is uncertain. We're estimating it. Okay? Take general chemistry lab if you use those things. Unless you just either don't need it or indifferent to it. Let's see. 124 is next. There we go. 124. Aluminum has a density of 2.70 grams per cubic centimeter. Notice, by convention, solids are the units of measure for solid density is grams per cubic centimeter. For liquids, it's grams per milliliter. That's just by convention. But in fact, they're exactly the same numbers. Grams per milliliter will be the same for aluminum as it is for any liquid. Okay, that's the density of aluminum. We want to know the mass of a rectangular block of aluminum measuring 11.1 by 22.2 by 34.5 centimeters. Okay. So, density is equal to mass per unit volume. We've got the density, and we can calculate the volume to calculate the mass. But what is the volume? Height times width times depth of a regular object, of a rectangular block. We can calculate that volume. So the volume would be 11.1 times, that's centimeters, times 22.2 centimeters times 34.5 centimeters. Okay, that's our volume, cubic centimeters. So why don't we just make it all one calculation? There's our volume. What's the mass? We don't know. But that's equal to the density, 2.70 grams per cubic centimeter. So cubic centimeters here, cubic centimeters in the denominator here, good. Grams here, grams there. So in order to solve this problem, we need to say mass is equal to 2.70 grams per cubic centimeter times 11.1 centimeters times 22.2 centimeters times 34.5 centimeters. Right? I just moved this whole thing up there and solve for this one. So now all we have to do is multiply that times that times that times that. And this is cubic centimeters, and centimeters times centimeters times centimeters is centimeters cubed. So this units cancels that units. Remember, when you do a calculation, you don't just multiply, divide, add, subtract the numbers. You do it to the units too. So, let's see, we're supposed to go till 11, right? All right, let me see how many more I got to go. Be sure I don't run out of time. Rather than do that calculation, the answer is 23.0 kilograms. Oh, I better do it because we've got different units. Notice we've got kilograms here, and we've only got grams there. So let's do this. 2.7, 11.1, 22.2, 34.5. There you go. So how many kilograms is that? Since our answer is in kilograms, we have to say, all right, how many kilograms is that? Well, you can say, we want to store up in a prefix of grams, 1,000, right? Kilo, store that up. So 1, 2, 3. 2.2954 kilograms. And then we can keep 3 significant figures. So this is 5. That becomes 10. We got 2.30 kilograms. Oops. Oh, I'm sorry. Move my decimal place to the wrong place. 23.0 kilograms. Here we go. So nobody stopped me yet. So either you know this stuff or you're just numb. Okay, 24, 32, 132. Here we go. Convert minus 47.9 degrees Celsius to Fahrenheit. We've already done one like this. What I would say with this one to watch out for is that negative sign. But be sure you take into account that. Because when you plug it into that formula, minus 47.9 plus 32. If you forget that negative sign, then you're going to maybe add it to 32 instead of subtract. And most multiple choice, good multiple choice questions have taken into account the most common mistakes that are made. And an answer is placed in those multiple choice that corresponds to that mistake. So just because you find it there doesn't necessarily mean it's the right answer. Because if you say plus 9/5 times that and add it to that, you're going to end up with maybe one of these others. Okay, just be aware. First of all, does it make sense? If you've got a minus, remember when we did that calculation, is the number, the value for Celsius and Fahrenheit exactly the same? Minus 40 degrees Celsius is equal to minus 40 degrees Fahrenheit. So this is pretty close, right? So you should expect to find minus something here. Maybe, right, that wouldn't be as too much. It won't be positive. That was too much. So it'd be either this one or that problem. So you'd have to do the calculation to find out which one's which. And if you come up with an answer that's in this neighborhood, then by estimating what you know about the relationship here, minus 40 and minus 40 are equal, that if your answer is one of these others, then you're probably wrong. Go back and check your calculations. 133. Which of the following involves no chemical change? Only physical change. Bake a cake? Oh yeah. You're going to have probably baking powder in there, and it'll decompose into gas, make it expand a little bit. Boiling water. That's a physical change, definitely physical change. And you don't have any of the oddballs down here. So you can stop there. That's your answer. Lighting match, burning paper, driving car, those all involve chemical changes. So 133 is B. That'll take you all 5 seconds to answer that one. 134. Yep. Copper has a density of 8.96 grams per cubic centimeter. If a cylinder of copper weighing 34.94 grams is dropped into a graduated cylinder containing 20 milliliters of water, what will be the new water level? Okay, so this is like that previous irregular object, only it's just working at it from a different angle. So if we know density is that, then this is equal to mass per unit volume. What else are we given? 34.94 grams. So we're given this one. Okay, so we can solve for volume. This volume is 34.9 grams divided by 8.96 grams per centimeter. Okay. So that'll give us the volume of the object of that copper cylinder. Which is 26.2 cubic centimeters, or 26.2 milliliters, exactly the same. Right? This is the volume of the object. If we drop that object into 20 milliliters of water, what will be the new height? Let's see, graduate some. Let's see, did I do that right? Yeah, 26.2. Maybe I didn't do that right. 34.94 grams. 8.96. Oops. It's not right. So I did some estimation in my head. It's just not working. 34.9, 8.96, 3.895. Okay. So that's the amount of volume that was added to the previous volume of 20. So it'll be 23.895. Or round it off. 23.90. That's the best answer. That's the new volume because we added an object to it and made it, we displaced it. Okay? Are we okay? All right. Let's see, this is Thursday. We have an exam on Tuesday. Yeah. Okay. So if you need help, right? Monday I have office hours, but if you need help on the weekend, just let me know. We can Zoom. Let's see. 1:37. Got 15 minutes left. Let's see if I can get these knocked out. 137. There we go. How many significant figures are in the number 4.00700 times 10 to the 13th, is it? Yeah. So we only have to look at this part. 1, captive zeros, 2, 3, 4, 5, 6, because there's a decimal. So there's 6 significant figures. Okay. Let's see, 138. I need to scroll for this one. All right. Which of the following is not a step in the scientific method? All right. What would be the first step in the scientific method? Observation. You see something that piques your curiosity. You want to know what the hell's going on. So you observe. Right? Then what? You speculate. You say, I think this is happening. This is what's going on there. That's known as hypothesis. And then you experiment to test your hypothesis to see if it is correct. Right? You design the experiment preferably so that you limit the changes that can occur when you apply a variable of some kind. So you have controls, right, that you do nothing to. You say, this is what it is. So in the process of the experiment, I can refer to this one and say, okay, nothing's happened to this one yet. Something's happening over here because of what I did to it. That's the experiment. Okay, so we got make an observation, formulate a hypothesis, perform an experiment, develop a theory, possibly. This will get you a law. But if you combine many experimental results, sometimes you can develop a theory. So the only one left is change the results to agree with your hypothesis. Believe it or not, some scientists do that. And when they're caught, their career is over. Preferably, we catch them in graduate school before they have a chance to get out and do some real damage. But then their advisor has to answer too. You let them get away with this, maybe your career is jeopardized too. I remember one famous, let's see, I got time. One famous, well, actually, it wasn't really a falsification of data. It was just poor experimentation. These two guys in Colorado claimed that they had produced cold fusion, benchtop fusion. And they said, and they were basing their results upon measurements of neutron flux. They're measuring the amount of neutrons coming from the experiment. And so in good review methodology, when they published their work, anybody else could take their work and duplicate it. And lots of people tried, and nobody could duplicate it. But this one scientist said, here's what I think is happening. So he designed his experiment to take into account stuff that they had missed, and found that they were not measuring neutron flux from their experiment. They were measuring it from an external source. So when he published his work, it tanked their experiment and their careers. Okay, let's see. What do I have next? 148. An example of a mixture. So we are getting some redundancy here. An example of a mixture. Gold is an element, right? Can't be a mixture. Air in this room. Yeah, that's a mixture. In fact, it's a solution. Purified water, that's a pure substance. Hydrogen fluoride is a compound. So all of these can't be, because we did find only one mixture, and the rest of them are not mixtures. So the air in the room is a mixture. 149, I think, is the next one. Yeah, 149 and 150. So 149, how many of the following are compounds? What's the definition of a compound? Well, when we write it out this way, it's got to have 2 or more elements in it. So we look at it. Okay, here's one, H2O, that's water. I saw this description, little flyer circulating many years ago. It was called something like the dangers of dihydrogen oxide. And it went through this long list of stuff. It was poking fun at the environmentalists. It's talking about water, right? Dihydrogen oxide is water. Dinitrogen tetroxide is a compound. Sodium hydroxide is a compound. Manganese dioxide is a compound. And hydrogen fluoride is a compound. They're all compounds. So there are 5 of them there. 150. Let's see, I'm going to have to scroll that one. How many of the following are pure compounds? Okay, now we're just giving names. Sodium, you can find that one on the periodic table. That's an element, not a compound. Oxygen is an element, it's not a compound. Iron's an element. It's an element, not a compound. Air is not a compound. It's a mixture of elements. The only one that is a pure compound is sugar. Right. So there's only one of them. Alrighty. Coming down to the wire here. 154. We're going to beat this horse some more. Helium is an example of what? Well, if you can find it on the periodic table, it's what? It's an element. Simple as that. 156. Which of the following is an element? All right. Can you find it on the periodic table? No. Water? No. Earth? No. Salt? No. Brass? No. Oxygen. So I did allow some redundancy into this review. 161. What is the result of the following multiplication expressed in scientific notation to the correct number of significant figures? Okay, so you do have to do this. 5.46 times 10 to the third and multiply that times 8.0 times 10 to the minus 3. Okay. So if you have your calculator, you just punch in those numbers and then you apply the rules, right? 2 significant figures, 3. We're limited to 2 significant figures in our answer, right? So if I don't have my calculator, can I pick the right answer out of this bunch? Well, first of all, same base, 10, 10. 3 plus minus 3 is 0. So this part here gives me 1. 10 to the 0 is 1. So how about this one? 8 times 5.5. Well, let's see. 8 times 5 is 40. And a half of 8 is 4, so it's like 44. But I can only have 2 significant figures, right? So 44 is pretty close. Here we go. So scientific notation, it would be 4.4 times 10 to the first, but, well, actually, that's a good answer. So you can do that one in your hand if you want, or you can use your calculator, right? If you're taking a test, maybe you're saturated and you need to rely on technology to help you through. That's okay. But this is what you should get. 4.4 times 10 to the first is 44. Uh, 169. I think this is the last one I have picked out. There it is, 169. And yeah, we're good. We've got 4 minutes left. A blank change involves a change in fundamental components of the substance. A given substance changes into a different substance, right? By definition, that is what type of change? That's a chemical change. You're changing the identity of the substance. So it's a chemical change. Okay. And that's all I had, unless you guys have questions, concerns, complaints, whatever the case may be. And I got 1 in seat and 2 on Zoom. All checked off. Okay. We'll see you on Tuesday for an exam. What we're going to do is, where is it? Here it is. Let me look back at the course schedule. If I can find it. Here we go. So the course schedule says there's our review. Homework on chapter 1, 2, and 3 is due on that day by midnight. The exam, if you're in seat, you'll take it right here in person. If you're taking it online, then you just need to complete it by midnight. There's also a syllabus test, right, that you get 1% for. And then we're going to jump into chapter 4. So since we've got 2 hours, well, about an hour for the test, and then chapter 4 we'll cover. So if you're taking it online, then what you may do is check in at the usual time and then just kind of hang around until I start off on the lecture for chapter 4. Because I don't know when that'll be. Whoever shows up in person, right now it's only 1. But once you're finished, then we'll go immediately into chapter 4. So if you're not there and watching periodically, then I might get started and you'll be left behind. Okay. So that's it for today. All right. Contact me if you need help.